AKA, let's see if you remember anything from first semester. Okay? I have faith.
Inertia.
All right, what's the first thing?
Object in motion tends to stay in motion unless acted upon.
Yeah, and I heard some people say inertia. Yes, so the first law is the law of inertia. Objects in motion remain in motion. Objects at rest remain at rest unless acted on by non-zero net force. So, we've talked about momentum already this unit, and we gave the definition of momentum being inertia in motion. So it's a way to quantify inertia. If an object is not moving, its inertia in motion is 0. If it is moving, you multiply its mass and velocity. In other words, P equals mv. And bingo, you have how Newton's first law relates to momentum. This is a visual way, a mathematical way to describe inertia. It's inertia in motion. So you can talk about the inertia in motion of objects, and you can quantify them. You can mathematically solve and calculate what they would be. So there's not a good way to do that without momentum. And so this is a way to kind of calculate that and put that all in one place. But one thing to mention is it's inertia in motion unless acted on by an outside force. What do we call that outside force when it acts for a period of time? We've talked about it this unit.
Momentum.
No, good guess. Impulse. 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 So, Newton's first law is objects in motion remain in motion. Objects at rest, that would be a momentum of 0, remain at rest unless acted on by an outside force called impulse. So there you go. All things that we've talked about from this unit. So there's the first law, taken care of, zipped up, bow tied, all that good stuff. Okay? Oh, good. We're in good shape. All right, Newton's second law. Who remembers Newton's second law? Yes?
Acceleration is directly proportional to net force inversely proportional to mass.
Yes. In other words, F equals ma. So we've talked about inversely proportional to mass, so more mass means less acceleration. Directly proportional to force, so more force means more acceleration. It's F equals ma. But let's look at this equation a little bit. So force is equal to mass times acceleration. Well, acceleration is a change in velocity over time. And it's a Monday. I don't like dividing on Mondays. So I'm going to multiply time to both sides. So we got force times time equals mass times velocity change. Oh, mass and velocity, that's momentum. But it's not a change in, it's not velocity by itself, it's a change in velocity. So F T equals delta P. That's where y'all go, whoa! Nope, no one's feeling that way. Oh, there we go. I got like 3 out there from people I guilted into doing it. Hey, it's that equation we just did last week. So you've already seen this equation. It's F equals ma, just done a little bit differently. Instead of doing it in terms of force and acceleration, you're doing it in terms of impulse and momentum. So basically, we're trying to keep all of the things together. We're trying to do everything in terms of momentum. Instead of having inertia for one thing, and then acceleration for another thing, and then force for a third thing, we're doing everything in terms of momentum. So momentum is inertia in motion. Change of momentum is done by an impulse. And then we get to the third law. So who remembers the third law? We're on a great streak. One more, please. Yes, every action has an equal and opposite reaction. Excellent. You had the same idea too. Every action has an equal and opposite reaction. So I'm just going to write equal and opposite reactions. Okay. Every action has an equal and opposite reaction. I want to show you something. I told you one of the definitions was in the absence of an external force, total momentum change is 0. So in other words, every action has an equal and opposite reaction. So the action is to change the momentum of 1, and the reaction is a negative change in the momentum of 2. And I know you're saying to yourself, okay, Mr. B, that's sweet, but that's literally nothing we've done. Like, I don't see what's going on here. Well, change in momentum 1 would be final minus initial. So momentum 1 final minus momentum 1 initial. And that would equal negative change in 2. So that's momentum final of 2 minus momentum initial of 2. I sure can. Yep. No, that's PF1 and that's P1. So it's PF1 and P1I. That's a 1. Okay. Let's get the initials together and let's get the finals together. So I'm going to distribute this negative sign. Okay, so this negative sign is going to go here. This negative is going to turn into a positive. So I'm going to subtract the initial of 2. I'm going to subtract the final of 1. I'm going to get negative P1 initial minus P2 initial equals negative P2 final minus P1 final. Get rid of all these negatives. Get rid of all these negatives.
I know
You gotta get the peck out of your step.
Fair enough.
I don't even understand half of this.
P1, well, it's going to be really clear in a second. Oh my gosh, it's the equation I gave you at the beginning of the period.
What do we gotta write though?
This. I want you to write this. Write this, equal and opposite reactions. Write this first part of the equation.
Don't see it.
Positive change in 1 equals negative change in 2. And then write that it turns into this. It turns into momentum of 1 initial plus momentum of 2 initial equals momentum of 1 final plus the momentum of 2 final. Yeah, there's one right outside the door.
Like all these papers, I can't.
Yeah, that's fine.
Too fast.